In today's documentary, we are going to discuss something that every physicist alive has been told is impossible. We are going to talk about traveling faster than light. In the year 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that would collectively change the course of human history. His name was Albert Einstein. One of those 4 papers was called On the Electrodynamics of Moving Bodies. In it, Einstein did something that no physicist before him had done. He took 2 observations about the physical world, 2 observations that seemed completely separate and unrelated, and asked what the universe would have to look like if both of them were true at the same time. The first observation was this: the laws of physics are the same for everyone who is moving at a constant speed. If you are on a train moving at 100 kilometers per hour and you drop a ball, the ball falls straight down, just as it would if you were standing still on the ground. You cannot feel your own motion when you move at a constant speed. There is no experiment you can do inside your train car with the windows closed that will tell you whether the train is moving or standing still. This was not new. Galileo had said something very similar 300 years earlier. The second observation was the strange one. For decades before Einstein, physicists had been trying to figure out what light actually was. James Clerk Maxwell had written down a beautiful set of equations in the 1860s that described light as an electromagnetic wave, a wave of oscillating electric and magnetic fields propagating through space. Maxwell's equations were extraordinary. They described electricity, magnetism, and light all in one unified mathematical framework, and they were incredibly accurate. But those equations contained something deeply uncomfortable. They predicted a specific speed for light in a vacuum, approximately 299,792,458 meters per second. And they gave no indication that this speed was relative to anything. They just stated it as a fixed number. This was a problem, because if the speed of light is fixed, then what happens when you, the observer, are moving toward or away from a source of light? If you are running toward a light source at, say, 10 meters per second, does the light hit you at its usual speed plus 10? If you are running away from it, does the light chase you at its usual speed minus 10? That is how it would work with sound. If you run toward a speaker, the sound waves hit you at a higher rate. If you run away, at a lower rate. But light seemed to refuse to play by those rules. In 1887, 2 American physicists named Albert Michelson and Edward Morley performed an extraordinarily careful experiment. They tried to measure whether the speed of light changed depending on the direction it was traveling relative to Earth's motion through space. They used an instrument called an interferometer that could detect changes in the speed of light, far smaller than any other device of the era. The result was 0. No matter which direction they pointed their apparatus, no matter how Earth was oriented relative to its orbit around the Sun, the speed of light was the same. It did not matter if they measured light going in the direction Earth was moving through space or perpendicular to it. The number came out identical. This should have been impossible. And for nearly 2 decades, nobody knew what to do with it. Einstein did. He took both observations that the laws of physics are the same for all constant speed observers, and that the speed of light is always the same no matter who measures it. And he decided that both must be true simultaneously. He refused to throw one of them out. He just asked, what does that mean for the structure of space and time? The answer was breathtaking. If the speed of light is the same for everyone, and if the laws of physics are the same for everyone, then space and time cannot be fixed, universal constants, the way Newton thought they were. Instead, space and time must bend and flex to accommodate the requirement that light always travels at the same speed. Here is the simplest way to see this. Imagine two observers. You are standing still. Your friend is in a spaceship flying past you at half the speed of light. You both watch a pulse of light travel from a laser to a mirror a kilometer away. For you, the light goes in a straight line. 1 kilometer there, 1 kilometer back. 2 kilometers total at the speed of light. Simple. For your friend in the moving spaceship, the light does not travel in a straight line. Because the mirror is moving along with the spaceship, the light has to travel in a diagonal path to catch up with the moving mirror. The total distance the light travels, from your friend's perspective, is longer than 2 kilometers. But the speed of light is the same for both of you. If the distance is longer but the speed is identical, then the time must be longer. Your friend's clock must be ticking more slowly than yours. This is not an illusion. It is not a trick of perception. It is a real, measurable, experimentally confirmed fact. Moving clocks actually run more slowly than stationary ones. This effect is called time dilation, and we have measured it with atomic clocks on airplanes, with clocks in GPS satellites, and with cosmic rays hitting Earth's atmosphere. It is real. And the same logic applies to length. An object moving past you is actually shorter in the direction of motion than it is when it is stationary. This is called length contraction. Also real, also measured. Now here is where the speed of light becomes not just a fast speed, but an absolute cosmic limit. Einstein's equations showed that as an object with mass accelerates toward the speed of light, two things happen simultaneously and inescapably. First, time for that object slows down relative to the outside world. Second, its effective mass, technically called its relativistic mass, increases. The more momentum you give it, the harder it is to accelerate further, because it keeps getting heavier and heavier in a relativistic sense. The mathematics is precise. The energy required to accelerate a massive object is given by Einstein's formula for relativistic kinetic energy. As the velocity approaches the speed of light, the denominator of that formula approaches zero. A denominator approaching zero means the quantity is approaching infinity. It would require an infinite amount of energy to accelerate any object with mass to exactly the speed of light. Infinite, not a very large number. Not a number so big we could never practically reach it. Infinite. This is why the speed of light is a wall and not just a speed bump. It is not that we do not have a big enough engine. It is that the universe's accounting system, the mathematical relationship between energy, mass and velocity, simply does not allow it. The closer you get to light speed, the more energy you need to go even a tiny bit faster. And the curve goes to infinity before you ever reach it. So there it is, the wall. Now, here is the question that physicists began asking starting in the latter half of the 20th century, and the question that drives everything we are going to discuss for the rest of this film. What if you did not try to go through the wall? What if instead you went around it? Einstein's special theory of relativity, the one we just talked about, applies to motion through flat, undisturbed space-time. It says nothing can go faster than light through space-time. But Einstein's general theory of relativity, published in 1915, does something more. It describes how space-time itself curves and bends in the presence of mass and energy. It allows space-time to be a dynamic, flexible structure that responds to what is inside it. And here is the critical question. Does the speed limit apply to space-time itself? Can space-time move faster than light? Before we talk about anything theoretical or unproven, let us talk about something that is unambiguously happening right now, that has been measured with extraordinary precision, and that appears to involve motion faster than light. The universe is expanding. This is not controversial. It is one of the most well-established facts in all of cosmology. In 1929, astronomer Edwin Hubble discovered that galaxies are moving away from us, and that the farther away they are, the faster they are receding. This was the discovery that proved we live in an expanding universe, that the Big Bang happened, and that the cosmos has a history. But here is the part that is less often talked about. The expansion of the universe is not like explosion debris spreading outward from a center point. It is not that the galaxies are flying through space away from each other. Rather, the space itself between them is stretching. Every point in space is moving away from every other point, not because anything is traveling through space, but because space itself is growing. Now consider what this means for very distant galaxies. Close galaxies are receding from us relatively slowly. Galaxies 1 billion light-years away are receding faster. Galaxies 2 billion light-years away faster still. At some distance, a distance we have actually calculated and measured, galaxies are receding from us so fast that light from those galaxies can never reach us. They are receding faster than the speed of light. The boundary at which this happens is called the Hubble sphere, and it lies at a distance of roughly 14 billion light-years from us. Beyond that sphere, the expansion of space carries galaxies away faster than light. We cannot see them. We cannot receive any signal from them. We are permanently cut off. But here is the thing. Those galaxies are not violating special relativity. Nothing is moving through space faster than light. The space between us and those galaxies is simply getting bigger, and it is getting bigger fast enough that the cumulative effect is a recession speed exceeding light. Space itself is not bound by the speed limit. The speed limit applies to things moving through space, not to space itself moving. This is the first and most important crack in the wall. The universe itself, in its large-scale expansion, provides a precedent that space-time is not bound by the speed of light. Space-time can do things that would be forbidden if matter tried to do them by accelerating through undisturbed space. This observation, that space itself can expand faster than light, is the foundational idea behind the single most famous and most seriously studied proposal for faster-than-light travel in the history of physics. What if you could make space expand and contract locally? What if, instead of moving your spaceship through space, you could move the space around your spaceship? In 1994, a young Mexican physicist named Miguel Alcubierre was sitting at his desk at the University of Wales working on problems in general relativity. He was also a science fiction fan, a fan of Star Trek specifically, which had featured its own fictional warp drive for decades. Alcubierre decided to ask a precise mathematical question. Is there any solution to Einstein's field equations, the fundamental equations of general relativity, that would produce motion resembling a faster-than-light warp drive? Not by accelerating a spaceship through space, but by warping the space itself around it. He found one. The paper he published in 1994 in the journal Classical and Quantum Gravity was not a long paper. It was about 10 pages. But those 10 pages changed the entire landscape of theoretical discussions about faster-than-light travel. The concept Alcubierre described works like this. Imagine your spaceship sitting in a flat region of space-time. Nothing special happening. Now imagine creating a distortion in the space-time around the ship. Not inside the ship, but outside it, in the fabric of space itself. Specifically, compress the space-time directly in front of the ship and expand the space-time directly behind it. When you compress space in front of the ship, you are essentially folding space so that the destination is now much closer than it was before. When you expand space behind the ship, you are stretching the space that was behind the ship, pushing it further away. The net result is that the ship, riding in the middle of this distortion, what Alcubierre called a warp bubble, moves toward its destination. And here is the crucial point. The ship itself is not moving through the space inside the bubble. Inside the bubble, the ship is essentially stationary. It is the bubble itself, the distortion in space-time, that is moving. And since the bubble is a distortion of space-time itself, not an object moving through space-time, it is not subject to the speed of light limit in the same way. The mathematics that Alcubierre wrote down express this using what is called a metric, a mathematical object in general relativity that describes the geometry of space-time at every point. His metric, written in full, involves a function called the shape function and a velocity function, and what it says is essentially this. At any given time, the region of space around the ship is distorted such that the distance from the ship to its destination is dramatically reduced. The ship effectively surfs a wave of space-time, just as a surfer rides a water wave. The surfer does not power through the water by their own effort. The water under the surfer moves, and the surfer is carried along. In the Alcubierre drive, space-time is the water, and the warp bubble is the wave. From the outside, Watching the ship with a telescope, you would see the ship accelerate from standing still to a velocity faster than light, travel to its destination, and stop. From the ship's perspective, you would feel nothing. No crushing acceleration, no g-forces, no time dilation. Inside the bubble, space-time is flat. You are in free fall. You simply feel as though you're sitting still while the universe rearranges itself around you so that your destination comes to you. This is genuinely remarkable. Einstein's own equations, used correctly, produce a solution that allows apparent faster-than-light travel without violating special relativity. The ship never locally exceeds the speed of light. It just rides a distortion that effectively moves it faster than light would travel the same route through undistorted space. The physics community was genuinely excited about this paper, not because anyone thought we could build it tomorrow, but because the mathematics was rigorous, the solution was consistent with known physics, and nobody could immediately find a fundamental objection that ruled it out. But then people started looking more carefully, and the problems began to emerge. The first and most devastating problem is energy. To create and maintain the warp bubble, the distorted region of space-time around the ship, you need to arrange matter and energy in a very specific configuration. And when Alcubierre and others did the calculations, the amount of energy required was astronomical, in the literal sense. Alcubierre's original calculations suggested that creating a warp bubble even a few meters across would require energy equivalent to the mass energy of a planet the size of Jupiter. Mass energy, remember, means E equals mc squared, the total energy locked inside a given mass if you converted all of it to energy. Jupiter's mass energy is approximately 1.9 times 10 to the power of 44 joules, which is about 125 septillion times the total energy output of the Sun in 1 year. To put that another way, the entire energy budget of the Sun over its entire 10 billion year lifetime would not come close to the energy needed to run a Jupiter mass warp drive. Later refinements of the calculation, including significant work by physicist Harold Sonny White at NASA, proposed ways to reduce this energy requirement substantially. White argued that by changing the shape of the warp bubble from a sphere to a torus, essentially a donut shape, and by oscillating the bubble's intensity, the energy requirement could potentially be reduced to something closer to the mass energy equivalent of a few hundred kilograms. That is still enormous by human engineering standards, but it is not infinite, and it is at least conceivably within the realm of advanced technological civilization. However, White's calculations were themselves later criticized by other physicists who found errors in the approximations he used. The question of the true minimum energy requirement for an Alcubierre drive remains genuinely open and actively debated. The second problem is worse. The Alcubierre drive does not just require energy. It requires a specific kind of energy, one that does not appear to exist in any form we have ever been able to produce or sustain in large quantities. To understand what kind, we need to understand how space-time curvature works. In general relativity, positive energy density, the energy of ordinary matter, ordinary light, ordinary radiation, causes space-time to curve in a specific way. It creates what physicists call attractive curvature. Positive energy bends space-time toward itself. This is why gravity pulls things together. Mass and energy create a gravitational field that pulls other mass and energy in. The Alcubierre drive requires a region of space-time to be compressed in front of the ship. Compression of space-time is the opposite of the expansion you get with positive energy. To compress space-time ahead of the ship, you need something with the opposite effect. Something that pushes space-time outward rather than pulling it inward. This is called negative energy density, and the material that would produce it is called exotic matter. Exotic matter is not antimatter. Antimatter exists. We make it in particle accelerators. Antimatter has positive energy. It falls downward in a gravitational field just like ordinary matter, and it is annihilated when it meets regular matter. Exotic matter would be fundamentally different. It would have negative energy density, meaning it would actually have less energy than empty space. Empty space, according to quantum field theory, has a certain baseline energy level. Exotic matter would have an energy level below that baseline. Does exotic matter exist? Here is the complicated answer. In quantum mechanics, there is a phenomenon called the Casimir effect. This was predicted theoretically in 1948 by Dutch physicist Hendrik Casimir and confirmed experimentally in 1997. If you take two parallel conducting plates and place them extremely close together, within a fraction of a micrometer, a measurable attractive force appears between them, pulling them together. The explanation involves quantum field theory. Empty space is not truly empty. It is filled with quantum fluctuations, pairs of virtual particles that pop into existence and annihilate almost immediately, a constant churning of energy at the quantum scale. These virtual particles exist across a spectrum of wavelengths. Between the two closely spaced plates, only virtual particles with wavelengths shorter than the gap can exist in the space between the plates. Outside the plates, all wavelengths can exist. This means there are more virtual particles outside the plates than between them, creating a net pressure that pushes the plates together. The region between the Casimir plates has a lower energy density than the surrounding vacuum. It has technically negative energy density relative to the vacuum. This is real. This is measured. This happens. The problem is scale. The Casimir effect produces negative energy densities that are unimaginably tiny. We are talking about energy densities of around -1 × 10 to the -3 joules per cubic meter under the most optimistic laboratory conditions. The amount of negative energy density you would need to sustain an Alcubierre warp bubble is many, many orders of magnitude larger. And physicists have also derived what are called quantum inequalities, theoretical limits on how much negative energy can exist in a given region of space for a given period of time. These inequalities, if they hold up in a full quantum gravity theory, effectively forbid the kind of sustained, large-scale negative energy density that the Alcubierre drive requires. The universe seems to have built-in circuit breakers that prevent exotic matter from accumulating in the quantities needed. The third problem is what physicists call the horizon problem, and it might be the most subtle and most damaging of all. Once you are inside an Alcubierre warp bubble moving faster than light, you cannot control the bubble. Here is why. The bubble is created by a specific arrangement of exotic matter outside the ship, in the wall of the bubble itself. To adjust the bubble's speed or direction, you need to change that arrangement. But the bubble is moving faster than light, which means no signal from inside the bubble can ever reach the front wall. Information from inside the bubble travels at the speed of light, and the front wall is always moving away faster than light. The pilot is completely cut off from the ability to steer the ship. There is also a second aspect of this problem. The pilot could not see what is in front of them. Light from the space ahead of the ship would be unable to enter the bubble. It would be swept up into the expanding region behind the ship before it could cross the bubble wall. The pilot would be flying blind through the universe at faster than light speeds with no way to steer or observe. That is an engineering problem that, at present, has no known solution. There is also a fourth problem: radiation. A theoretical analysis performed by physicists Stefano Finazzi, Stefano Liberati and Carlos Barcelo in 2009 showed that the interior of the Alcubierre bubble would be bathed in intense, lethal radiation generated by quantum effects in the bubble walls. This is related to the Hawking radiation that black holes emit. The bubble walls create horizons similar to those of black holes, and those horizons should radiate. The people inside the bubble might be cooked by their own faster-than-light drive. And finally, the fifth problem: time travel. If you can travel faster than light in one direction, special relativity shows that there exists some reference frame in which you actually arrived before you left. Faster than light travel, in the framework of special relativity, is mathematically equivalent to travel backward in time from certain perspectives. This creates what physicists call closed time-like curves, paths through space-time that loop back on themselves, allowing you to visit your own past. This leads to causality paradoxes. What happens if you go back in time and prevent the event that caused you to take this particular trip? The question of whether the laws of physics ultimately forbid time travel, and therefore forbid faster-than-light travel, is called the chronology protection conjecture, proposed by Stephen Hawking in 1992. Hawking argued that the laws of physics would always conspire to prevent true time travel from becoming possible. But this conjecture remains unproven. We do not yet have a complete quantum theory of gravity, and without one we cannot definitively say whether chronology protection holds. So where does the Alcubierre drive stand today? It is a mathematically consistent solution to Einstein's field equations. It has not been ruled out by experiment, because no experiment we can do addresses the relevant energy scales. The problems with it are severe: extreme energy requirements, the need for exotic matter, the navigation problem, the radiation problem, and the causality problem. None of these has a known solution, But none of these is a proof that it is impossible. They are engineering challenges of almost incomprehensible difficulty. And in the history of physics, almost incomprehensibly difficult has occasionally turned out to be actually achievable. In 2024, a paper published in Physical Review D described how a collapsing warp bubble, a bubble whose drive failed, would emit gravitational waves. This was a significant theoretical development because it suggested that warp drives, if they were ever built by anyone anywhere in the universe, might be detectable from Earth using gravitational wave detectors. The fact that physicists are now thinking about how to detect warp drives built by other civilizations tells you something about how seriously some researchers take the underlying physics. The Alcubierre drive is not science fiction dressed up as science. It is science, hard, rigorous, difficult, potentially impossible science, but science. In 1915, the same year Albert Einstein published his general theory of relativity, an Austrian physicist named Ludwig Flamm was reading through a solution to Einstein's equations that a German soldier named Karl Schwarzschild had derived from a trench on the Eastern Front of the First World War. Schwarzschild's solution described the geometry of space-time around a perfectly spherical, non-rotating mass, a perfect mathematical point of infinite density that we would later call a black hole. His solution was the first exact solution to Einstein's equations, and he sent it to Einstein before dying of a disease he contracted at the front. Flamm looked at the Schwarzschild solution and noticed something strange. The mathematics described not one region of space-time, but two separate flat regions of space connected by a narrow bottleneck, like two funnels connected at their narrow ends. This was the first glimpse of what we now call a wormhole. In 1935, Einstein himself, working with physicist Nathan Rosen, formalized this structure. They called it an Einstein-Rosen bridge. They were not trying to propose a transportation device. They were trying to use the bridge structure as a mathematical description of fundamental particles. The idea that an electron might not be a true point particle, but rather a tiny bridge connecting two sheets of space-time. That idea did not work out. But the Einstein-Rosen bridge itself, the mathematical structure of a wormhole, turned out to be a real and persistent feature of general relativity. There was one catch. The original Schwarzschild wormhole, the Einstein-Rosen bridge, is not traversable. It collapses instantaneously. The throat, the narrow connecting region between the two sheets of space-time, pinches off faster than any object, even light, could pass through it. If you were to try to travel through a Schwarzschild wormhole, the throat would close and crush you before you made it halfway through. For decades, this appeared to be the end of the story. Wormholes existed in the mathematics of general relativity, but they could not be used for anything practical. Then, in 1987, a phone call changed everything. Carl Sagan, the famous astronomer and science communicator, was writing a science fiction novel called Contact. In the novel, an alien civilization sends blueprints for a machine that humans build, and the machine opens a wormhole to the alien star system, allowing humanity's first interstellar journey. Sagan wanted the physics of the wormhole to be at least approximately correct, so he called his friend Kip Thorne, one of the world's leading experts in general relativity at the California Institute of Technology. Thorne thought about it. Then he assigned the problem to a graduate student and collaborator named Michael Morris. Together, Morris and Thorne worked out the physics of what a wormhole would have to look like to actually be traversable, to stay open long enough and remain stable enough for a person or spacecraft to travel through it. Their 1988 paper in the American Journal of Physics, titled Wormholes in Space-Time and Their Use for Interstellar Travel, is now a classic of the field. Here is what they found. A traversable wormhole would have a structure like this: two openings, called mouths, connected by a narrow passage called the throat. The mouths could be separated by any distance, across the solar system, across the galaxy, across the universe. To travel from one mouth to the other, you would simply enter one mouth, traverse the throat, and emerge from the other mouth, arriving at your destination without having travelled through the intervening space at all. From the outside, this looks like faster-than-light travel. If one mouth of the wormhole is near Earth and the other is near Proxima Centauri, 4.2 light-years away, you could travel between the two star systems in the time it takes to traverse the throat, which could be seconds or minutes. While light travelling the conventional route through space would take 4.2 years, you have effectively travelled 4.2 light-years in seconds. The mathematics is perfectly consistent with general relativity. There is no obvious contradiction with special relativity because you are not moving through space at faster-than-light speed. You are taking a shortcut through a different part of the space-time manifold. But, and there is always a but, to keep the throat of the wormhole open, you need something that prevents it from collapsing. And what prevents it from collapsing, in the mathematical solution Morris and Thorne derived, is exotic matter. Matter with negative energy density. Here we meet the same villain we met in the Alcubierre drive. Exotic matter. The wormhole throat is under enormous gravitational pressure. Ordinary matter, with its positive energy density, curves space-time in a way that would cause the throat to pinch off and collapse. To prevent this, you need matter that curves space-time in the opposite direction, that pushes the throat open rather than allowing it to close. That requires negative energy density. The amount of exotic matter required is also substantial, though some estimates suggest it might be less than the amount required for an Alcubierre drive. Exactly how much depends strongly on the specific geometry of the wormhole, and physicists have proposed various modifications to the basic Morris-Thorne design that might reduce the exotic matter requirement. Now, here is where the story of wormholes gets even stranger and even more interesting. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a radical conjecture that has come to be written as ER equals EPR. ER stands for Einstein-Rosen, meaning the Einstein-Rosen bridge, a wormhole. EPR stands for Einstein-Podolsky-Rosen, referring to a 1935 paper in which Einstein, Boris Podolsky, and Nathan Rosen described what Einstein called spooky action at a distance, what we now call quantum entanglement. The ER equals EPR conjecture states that these two things, wormholes and quantum entanglement, are the same phenomenon, just viewed at different scales. When two particles are quantum entangled, they are connected by a microscopic, non-traversable wormhole. The entanglement is the wormhole, just at a scale so small it cannot be used for travel. This conjecture has not been proven, but it has generated enormous excitement and an enormous body of follow-up research because it suggests a deep connection between quantum mechanics and the geometry of space-time, a connection that, if understood properly, might tell us something fundamental about whether wormholes can exist and whether they can be stabilized. In 2022, a team of physicists at the California Institute of Technology performed an experiment that they described as a wormhole simulation using a quantum computer. They used a quantum processor made of 9 qubits to simulate the behavior of a simple quantum gravity system. And they were able to observe a signal that appeared to travel through the simulated system in a way that mimics the behavior of information traversing a wormhole. This was not a wormhole. It was a quantum simulation of the mathematical behavior of a system that is related to wormholes through the ER equals EPR conjecture. The quantum computer was not creating a passage through space-time. But what the experiment demonstrated was that the mathematical structure of wormholes, the quantum information physics of how information could be transmitted through them, can be studied and explored using quantum computers. This is significant, because one of the biggest obstacles to wormhole research has always been the fact that we cannot perform any experiments remotely close to the relevant energy and scale. Quantum computers offer a completely different path, simulating the relevant quantum gravity physics in a controlled laboratory environment. In 2026, just recently, new theoretical research published in Classical and Quantum Gravity proposed a new interpretation of the original Einstein-Rosen bridge itself. Rather than being a tunnel through space connecting two distant regions, this research suggests it may represent a connection between two complementary time directions in a quantum description of space-time. A forward-flowing and a backward-flowing component of a complete quantum state. This is a radical reinterpretation, and it may have implications for whether the original Einstein-Rosen bridge, properly understood in quantum terms, could be made traversable under a full quantum gravity theory. The key point is this: wormhole physics is alive. It is not a dead-end curiosity of pure mathematics. It is an active research field with experiments being performed, new theoretical proposals being published, and genuine open questions about whether the universe permits shortcuts through its own structure. But there is one more aspect of wormholes that demands attention, because it is the most philosophically disturbing thing we have encountered so far. Wormholes, if they existed and if they could be traversable, might also function as time machines. Here is how. Imagine you build a wormhole with one mouth near Earth. You then take the other mouth and accelerate it to a very high speed for a period of time, say close to the speed of light for several years, before bringing it back to rest. Because of time dilation, the moving mouth of the wormhole ages more slowly than the stationary mouth near Earth. When you bring the mouths back to the same location, there is now a time difference between them. The moving mouth is in the past relative to the stationary one. You could then travel through the wormhole from the present mouth to the past mouth and emerge at an earlier time. You would have travelled backward in time. This is not fiction. This is a consequence of general relativity and special relativity applied carefully to the wormhole geometry. Thorne himself worked through this possibility in detail in the late 1980s and found that it was mathematically permissible within the framework of general relativity. Whether the universe actually permits this, whether a full quantum theory of gravity would eliminate this possibility, or whether Hawking's chronology protection conjecture is correct, is unknown. But the mathematical possibility is real, and it adds another layer of profound strangeness to the wormhole story. Everything we have discussed so far involves manipulating space itself, warping it, tunneling through it, creating shortcuts in its structure. But there is an entirely different approach to faster-than-light travel, one that starts not from the geometry of space-time, but from the properties of matter itself. What if there were particles that did not just break the speed of light barrier, but were constitutionally incapable of going slower than light? This is the concept of the tachyon. The idea was first proposed seriously by physicist Gerald Feinberg of Columbia University in 1967. Feinberg pointed out a logical structure in Einstein's special relativity that nobody had fully explored. Special relativity says that you cannot accelerate a massive particle from below the speed of light to above it. The energy required to do so is infinite. You cannot cross the light speed barrier from below. But what if there were particles that started above the light speed barrier? What if they had always been there, already moving faster than light, and they could never slow down to below light speed, because that would require them to go through the same infinite energy barrier in reverse? This is what a tachyon would be. A particle that lives forever on the faster-than-light side of the barrier, just as ordinary particles live forever on the slower-than-light side. The mathematics of tachyons follows from Einstein's energy-momentum relation. In special relativity, the total energy of a particle is related to its rest mass and its momentum by the equation E squared equals P squared C squared plus M squared C to the fourth, where E is energy, P is momentum, C is the speed of light, and M is the rest mass. For ordinary particles, M is a positive, real number. For a particle to travel faster than light, its effective mass in this equation must be what mathematicians call imaginary. That is, the square root of a negative number. When you plug in an imaginary mass to the energy-momentum relation, you get a particle whose energy decreases as it goes faster, and whose energy would become zero only at infinite speed. A tachyon at infinite speed would have zero energy. A tachyon at rest, if such a thing were even meaningful, would have infinite energy. This means that unlike ordinary particles, which gain energy as they speed up, tachyons lose energy as they speed up. To slow a tachyon down to near the speed of light, you would have to add energy to it. To speed it up toward infinite velocity, you would have to remove energy from it. A tachyon that loses all its energy instantly accelerates to infinite speed and disappears. Now, imaginary mass sounds deeply strange. But imaginary quantities appear in physics all the time as mathematical devices, and what matters is whether the physical predictions of a theory with imaginary mass particles are consistent with observations. Here is where things get complicated. In quantum field theory, the framework that unifies quantum mechanics with special relativity, imaginary mass fields do appear, and they are not exotic curiosities. In fact, the Higgs field, the field responsible for giving elementary particles their mass, is technically a tachyonic field in a specific mathematical sense. The Higgs field started out as a tachyonic field in the early universe and then rolled down to a stable configuration, a process called spontaneous symmetry breaking that gave it the properties we observe today. So tachyonic fields, fields described by equations with imaginary mass, are real parts of established physics. The question is whether tachyonic particles, actual particles that travel faster than light through physical space, can exist. The current scientific consensus is that they do not. There are several reasons. First, tachyons would violate causality. Because of the way special relativity relates space and time, a tachyon traveling faster than light in one reference frame would be traveling backward in time in another reference frame. This means that if tachyons could be used to send information, you could use them to send messages to the past, creating the same causality paradoxes we discussed with warp drives. Second, extensive searches for tachyons have been performed. Tachyons with imaginary mass would have distinctive signatures in particle detectors, and no such signatures have been found. Third, theoretical analyses by physicists like George Sudarshan, Alexa Myron-Belaniuk, and others who attempted to formulate a complete, consistent quantum field theory of tachyons found severe difficulties. The interactions between tachyons and ordinary matter in these theories produced instabilities and inconsistencies. But here is the nuanced part of the story, and the reason tachyons have not been entirely dismissed. The tachyon concept has genuine mathematical content. There is a precise, well-defined mathematical description of what a tachyon would be. The obstacles to tachyon physics are not logical contradictions. They are physical problems, specifically the causality problem. And the causality problem, as we keep discovering in different forms, is something that we cannot definitively rule out or rule in without a complete theory of quantum gravity. Some physicists have proposed what are called reinterpretation principles for tachyons, ways of interpreting the tachyon's backward in time motion that avoid the causality paradox. The basic idea is that a tachyon being emitted in the forward direction of time is physically equivalent to a tachyon being absorbed in the backward direction of time. And if you always choose whichever interpretation avoids causality violation, you can construct a self-consistent framework. Whether this reinterpretation is physically meaningful or merely a mathematical trick remains debated. The search for tachyons continues quietly in the analysis of particle accelerator data. So far, no evidence. But absence of evidence is not evidence of absence, especially for particles that may interact very weakly with ordinary matter. Of all the phenomena in physics that seem to involve faster-than-light effects, quantum entanglement is the one that actually does occur, has been measured thousands of times, and is completely real. And yet it turns out to be both more remarkable and more frustrating than any of the hypothetical methods we have discussed. Let us explain what quantum entanglement actually is. In quantum mechanics, particles can exist in states that are not definite. A particle might be in a superposition of having spin up and spin down simultaneously until a measurement is made. When you measure it, it instantly collapses to one definite state. Now consider two particles that are created together in a process that conserves some quantity, say total spin. If one particle has spin up, the other must have spin down in order for total spin to be zero. But in quantum mechanics, until you measure either particle, neither has a definite spin. Both particles are simultaneously in a superposition of up and down. When you measure the first particle and find it has spin up, something happens to the second particle at that exact instant. It collapses to spin down. Not after a delay. Not after a light signal travels between them, instantly, no matter how far apart the two particles are. A centimetre, a kilometre, a light year, a billion light years. The measurement of one particle instantly determines the state of the other. This was the prediction of quantum mechanics that Albert Einstein found completely unacceptable. He called it spooky action at a distance, and spent years arguing that quantum mechanics must be incomplete, that there must be some hidden information, what he called hidden variables, that determined in advance what result each particle would give, and that the apparent instantaneous connection was just revealing that pre-existing information. In 1964, physicist John Bell derived a mathematical theorem, Bell's theorem, that made the hidden variables idea testable. He showed that any theory based on hidden variables would have to satisfy certain mathematical inequalities, called Bell inequalities, and that quantum mechanics predicted these inequalities would be violated. Experiments performed starting in the 1970s and most definitively in 2022, work for which Alain Aspect, John Clauser and Anton Zeilinger received the Nobel Prize in Physics, conclusively demonstrated that Bell's inequalities are violated in the real world. The experiments confirmed quantum mechanics and ruled out local hidden variable theories. The quantum connection between entangled particles is real. It is not explained by any pre-existing hidden information. When you measure one particle, something genuinely happens to the other particle, instantly, regardless of distance. In 2008, physicist Nicholas Gissin's group in Geneva performed an entanglement experiment where the two particles were separated by 18 kilometers and their measurements were made simultaneously within a precision that guaranteed any hidden signal between them would have to travel at least 10,000 times faster than light. The correlations still appeared perfectly every time, Whatever is connecting entangled particles is at least 10,000 times faster than light. And yet, you cannot use entanglement to send information faster than light. This is the maddening part, and it has a precise mathematical reason. When you measure your particle and get spin up, you cannot control the result you get. The outcome is random. Quantum mechanics gives you probabilities, not certainties. Your friend with the other particle also gets a random result. The key point is that each individual result, taken alone, looks completely random. It is only when you compare your results with your friend's results, a comparison that requires a conventional signal traveling at or below the speed of light, that you discover the correlation. You cannot force your particle to give a specific result. And since you cannot control the result, you cannot encode a message in it. The correlations between the two particles are real and instantaneous, but you cannot exploit those correlations to transmit controlled information without also transmitting a classical signal that reveals which results to compare. This result is formalized in what physicists call the no-communication theorem. Quantum entanglement cannot be used to transmit information faster than light. The theorem is a rigorous mathematical result within standard quantum mechanics. But, and this is perhaps the most thought-provoking point in this entire documentary, the no-communication theorem is a theorem within quantum mechanics, as we currently understand it. It assumes that the standard quantum mechanical framework is complete and correct. If there are aspects of quantum mechanics that we have not yet understood, if quantum gravity changes the picture at very small scales or very high energies, then, in principle, the no-communication theorem might not be the final word. What we can say with certainty is this: quantum entanglement demonstrates that nature has some kind of non-local connection, a connection that operates outside the bounds of what we think of as ordinary spatial distances. Understanding what that connection really is at a deep physical level is one of the most important open questions in all of physics. And the answer to that question might or might not have implications for faster-than-light communication. In 1962, a semiconductor engineer at Texas Instruments named Thomas Hartman was doing a calculation of how long it takes an electron to tunnel through a quantum barrier. He expected to get a straightforward result. What he got instead was so disturbing that it would generate decades of controversy in physics. The result he got suggested that particles tunneling through a quantum barrier can take less time to cross the barrier than light takes to travel the same distance through empty space. In other words, quantum tunneling appears to be faster than light. To understand what is happening, we first need to understand what quantum tunneling is. In classical physics, a ball rolling toward a hill will stop and roll back if it does not have enough energy to reach the top. Energy is everything. No energy, no passage. In quantum mechanics, particles behave like waves. Their position is described by a wave function that tells you the probability of finding the particle at any given location. When this wave encounters a barrier, an energy wall that the particle classically should not be able to cross, the wave does not simply stop at the wall. It decays exponentially inside the wall, but it does not reach zero before the other side. There is a small but non-zero probability of finding the particle on the other side of the wall, even though the particle never had enough energy to go over the wall. This is quantum tunneling, and it is not theoretical speculation. It is the mechanism behind nuclear fusion in the Sun. Without tunneling, hydrogen nuclei could never get close enough to fuse despite the thermal energy in the solar core. It is the mechanism behind radioactive decay. It is the mechanism behind the transistors in every computer and smartphone on Earth. Quantum tunneling is one of the most experimentally verified phenomena in all of physics. Now, Hartmann's disturbing finding. When he calculated how long a particle spends inside the barrier during tunneling, he found something called the Hartmann effect. The tunneling time appears to be essentially independent of the thickness of the barrier. Make the barrier thicker and thicker, and the tunneling time hardly changes. This means that for a sufficiently thick barrier, the particle appears to cross the barrier in less time than it would take light to cross the same thickness of empty space. This was confirmed experimentally in 1993 by Ephraim Steinberg, Paul Kwiat and Raymond Chow at the University of California, Berkeley. They sent photons through an optical barrier and measured the tunneling time. The tunneling photons arrived earlier on average than photons that traveled the same distance through empty space without a barrier. The average apparent speed of the tunneling photons was 4.7 times the speed of light. Similarly, in 1994, German physicist Günther Nimtz sent a recording of Mozart's Symphony No. 40 through a microwave barrier 27 inches wide and measured that the signal traversed the barrier at 4.7 times the speed of light. So, has faster-than-light travel been achieved? No, and the reason why requires careful thought. The issue is what exactly we mean by the signal travelling at 4.7 times the speed of light. When we say a signal travels faster than light, what matters for causality is not the average position of the wave peak, but the front of the wave, the very first moment that any part of the signal arrives at the destination. What Steinberg's experiment and Nimtz's experiment measured was the apparent motion of the peak of the wave packet. But the wave packet is not a precise, definite object with a sharp front edge. It is a broad, smeared-out quantum probability distribution. The apparent superluminal speed of the peak is not the same as the speed at which information arrives at the detector. Here is an analogy that physicists use. Imagine a very long cigar-shaped cloud. The center of the cloud is moving toward you, but the front tip of the cloud is already ahead of you. What you perceive as the cloud arriving might be its peak reaching you, but the very front of the cloud, the edge that carries actual information about the cloud's presence, was already there before the apparent peak arrived. The peak can appear to move faster than the actual front because the wave's shape is being reshaped as it interacts with the barrier. The more precise theoretical explanation involves what physicists call reshaping of the wave packet. The barrier preferentially transmits the part of the wave packet that arrives slightly earlier, so the transmitted packet's peak appears earlier than expected. But the actual front of the signal, the first photon, the first deviation from nothing, still travels at exactly the speed of light and carries no information faster than light can. This interpretation is supported by the no communication theorem and by the fact that you cannot use quantum tunneling to send a controlled message faster than light. In Nimtz's Mozart experiment, the recording emerged at the other side of the barrier, apparently at 4.7 times light speed. But the information about the exact shape of the signal, the information needed to actually hear the symphony, was already encoded in the shape of the wave before it entered the barrier. No new information was transmitted superluminally. However, and this caveat is important, some physicists are not fully satisfied with this explanation. The question of what exactly time means for a tunneling particle is one of the most subtle and unresolved questions in quantum mechanics. There have been at least 10 different theoretical proposals for how to define and measure the time a particle spends inside a quantum barrier, and they give different answers. In 2024, researchers at TU Darmstadt proposed a new method for measuring tunneling time using atomic clocks built into the tunneling particles themselves. Their preliminary calculations suggest that a tunneling particle actually takes slightly longer to emerge than expected, contradicting the idea of superluminal tunneling. But the time differences involved are so small, on the order of 10 to the minus 26 seconds, that direct measurement remains a heroic experimental challenge. The debate is not settled, and the fact that it is not settled, that one of the most basic questions about one of the most well-established phenomena in physics remains genuinely open, is a reminder of how much we still do not understand about the relationship between quantum mechanics, time, and the speed of light. In 1995, a Russian physicist named Sergei Krasnikov published a paper that took the Alcubierre drive concept in a different direction. The Krasnikov paper described a different way to use space-time distortion for faster-than-light travel, one that solved some of the navigation problems of the Alcubierre drive, while introducing its own fascinating complications. Krasnikov proposed what is now called the Krasnikov tube. The basic idea is this. Instead of surrounding your spaceship in a moving bubble of distorted space-time, you instead modify the space-time along your entire route as you travel outward from Earth to your destination. You leave behind a permanent tube of distorted space-time, a corridor, essentially, through which you traveled. This tube has a specific property. The effective travel time through it is much shorter than it would be without the tube. Here is the crucial difference from the Alcubierre drive. On the way out, the first trip to your destination, you travel at the speed of light or slower. You are not going faster than light on the outbound journey. As you travel, you modify the space-time behind you, building the tube. When you reach your destination and turn around, you come back through the tube at effectively faster than light speed. The tube remains in place permanently, or at least for as long as the exotic matter supporting its geometry is maintained. On future trips, you can travel in both directions through the tube at faster-than-light speeds. This solves the Alcubierre navigation problem. Inside the Krasnikov tube, you are not in a moving bubble. You are inside a fixed corridor of distorted space-time. You can see where you're going. You can receive light signals from the far end of the tube. You can steer. The energy requirements and the need for exotic matter are similar to the Alcubierre drive. You still need matter with negative energy density to maintain the distorted geometry of the tube walls. And the tube, once built, is a permanent structure in space-time. It does not go away when you arrive. This last point leads to a rather alarming consequence that physicist Matt Visser pointed out in the late 1990s. If you have two Krasnikov tubes, one from Earth to your destination and one from your destination back to Earth along a slightly different path, you have created the same kind of causal structure as two traversable wormholes. And as we discussed with wormholes, two such structures connected together can potentially be used to construct a time machine. The Krasnikov tube, like the Alcubierre drive, like the wormhole, runs into the same fundamental problem. Any device that enables faster than light travel may also enable time travel, and time travel creates causality paradoxes that may or may not be self-consistently avoidable. The Krasnikov tube is less famous than the Alcubierre drive and less celebrated than the traversable wormhole. But it occupies an important theoretical niche. It is a reminder that there are multiple distinct mathematical approaches within general relativity to the problem of faster-than-light travel, and that each approach has its own distinctive strengths and weaknesses. The space of possible solutions to Einstein's equations is vast, and we have explored only a tiny fraction of it. In 2020, a physicist named Eric Lentz published a paper in the journal Classical and Quantum Gravity that made headlines across the science world. The reason was simple. Lentz claimed to have found a warp drive solution to Einstein's equations that does not require exotic matter. This was, if true, an extraordinary breakthrough, because the need for exotic matter, matter with negative energy density, which may not exist in nature in sufficient quantities, is the single most fundamental obstacle to the practical realization of any warp drive. If you could build a warp drive without it, you would have eliminated the most basic physical barrier to the concept. How did Lentz do it? Recall how the Alcubierre drive works. It uses a specific space-time geometry, a specific arrangement of expanding and contracting space-time curvature to create a bubble. In Alcubierre's geometry, the energy density of the matter creating this curvature goes negative. This is not a choice Alcubierre made deliberately. It is an inescapable consequence of the specific shape of the space-time metric he used. Lentz looked at this problem from a different angle. He did not start with a particular metric and then ask what energy was needed. Instead, he searched the vast space of possible soliton solutions, self-contained, stable, moving structures, to Einstein's equations, and looked for ones that had only positive energy density. He found a new class of solutions he called positive energy warp geometries. In Lenz's solutions, the energy density and the space-time curvature are arranged differently from Alcubierre's design. Where Alcubierre separates the regions of high energy density from the regions of high curvature, Lenz's geometry correlates them. The high energy regions and the regions of strong curvature overlap. This correlated arrangement, Lenz showed, allows for a self-consistent warp bubble geometry that requires only positive energy densities. This sounds like exactly the breakthrough needed. So why have we not already started building it? Several reasons. First, while the energy in Lenz's solution does not require exotic matter, the total amount of positive energy required is still extraordinarily large, by initial estimates on the order of the mass energy of Jupiter, comparable to the original Alcubierre estimates. Subsequent analysis has suggested even larger energy requirements. There was no obvious reduction in the energy scale, just a different kind of energy. Second, other physicists analyzing Lenz's paper pointed out that while his solutions do not require bulk exotic matter distributed throughout a large volume, they may still require thin shells of matter at the bubble wall that violate energy conditions locally. The question of whether Lenz's solutions are truly exotic matter-free or just distribute the exotic matter differently is still being actively debated. Third, the Lenz solutions describe a stationary state, a warp bubble moving at a constant velocity. How you would create such a bubble from scratch or stop it once it is moving is not addressed in the paper and presents its own challenges. The Lenz warp drive is genuinely new physics. It represents a real expansion of the theoretical landscape of warp drive solutions, and it continues to be studied and refined by researchers in the field. It is not a solved problem, but it changed the conversation by demonstrating that the space of mathematically allowed warp geometries is larger than Alcubierre's original solution suggested. In 2021, a team at Applied Physics, the company co-founded by Alexei Bobrik and Gianni Martir, published a comprehensive framework for classifying all possible warp drive geometries in general relativity. Their framework showed that warp drives can, in principle, be constructed from positive energy only, but that any such drive would be subject to the same speed limit as ordinary matter. To break the speed of light barrier, you still need some violation of the energy conditions, some form of matter or energy that ordinary matter does not provide. This result was simultaneously disappointing and illuminating. It drew a sharper mathematical boundary around the problem. You can have warp drives without exotic matter, but they will not be faster than light. To go faster than light, you need exotic energy. The question becomes, does exotic energy exist? Can it be produced? And can it be controlled? So far, all of the approaches we have discussed operate within the 4 dimensions of space-time that Einstein described. 3 dimensions of space and 1 of time. But for the past century, theoretical physicists have been seriously exploring the possibility that our universe has more than 4 dimensions. The idea began with a German mathematician and physicist named Theodor Kaluza in 1921. Kaluza noticed something extraordinary. If you take Einstein's equations of general relativity and extend them to 5 dimensions, 4 of space and 1 of time, the extra equations you get from the 5th dimension look exactly like Maxwell's equations of electromagnetism. Gravity in 5 dimensions contains electromagnetism as a component. This was stunning. It suggested that gravity and electromagnetism, the two forces known in 1921, might be unified as a single force in a higher dimensional geometry. In 1926, Swedish physicist Oskar Klein explained why we do not perceive this 5th dimension. It is curled up into an incredibly tiny loop, so small that we can never directly observe it. The scale of this compactification is close to what we now call the Planck length, approximately 1.6 times 10 to the minus 35 meters, which is roughly 10 to the 20th power times smaller than the diameter of a proton. This Kaluza-Klein theory was the beginning of what would become, over the rest of the 20th century, an entire research program based on the idea of extraspatial dimensions. The most famous modern descendant of this idea is string theory, which requires not 5, but 10 or 11 total space-time dimensions for its mathematical consistency. The extra 6 or 7 dimensions are compactified, curled up at the Planck scale, which is why we do not see them. The implications for faster-than-light travel are interesting. If extra dimensions exist, even compactified ones, they represent structure in space-time that we do not currently account for in our travel calculations. If a shortcut exists through those extra dimensions, a path that takes you from one point in our 3-dimensional space to another point without traversing the full 3-dimensional distance, then you could effectively travel faster than light relative to the 3-dimensional space we inhabit. Think of it this way. You are an ant on the surface of a ball. To walk from one side of the ball to the other, you have to crawl all the way around the surface, a long journey. But if there were a tunnel through the interior of the ball, you could walk straight through and arrive at the other side in a fraction of the time. To an observer watching you on the surface, it would appear that you travelled much faster than you should have been able to. Extra dimensions might provide exactly this kind of shortcut. A path that appears to travel faster than light in our 3-dimensional world might actually be a path through extra-dimensional space that is shorter than any path constrained to our observable dimensions. In the late 1990s, theoretical physicists Lisa Randall and Raman Sundram proposed 2 specific models of extra dimensions, known as Randall-Sundram 1 and Randall-Sundram 2, that have been very influential. In these models, our universe is a 3-dimensional surface called a brane, embedded in a higher dimensional space called the bulk. Gravity can propagate through the bulk and off our brane, while the other forces, electromagnetism, the strong nuclear force, the weak nuclear force, are confined to our brane. In these models, the distance between 2 points on our brane, measured through the higher dimensional bulk, can be much shorter than the distance measured along the brane's surface. If you could somehow travel through the bulk, you could appear to move faster than light, as measured by observers on the brane. The problem is that we are apparently made of brain matter, matter confined to our 3-dimensional brane. We cannot freely enter the bulk any more than a two-dimensional being could spontaneously step into three dimensions. The forces that hold matter together, the electromagnetic force that makes atoms solid, the nuclear forces that hold atomic nuclei together, all of these operate on the brain and would prevent a macroscopic object from moving into the bulk. Whether there are any physical mechanisms that could allow bulk travel, or at least allow information to travel through the bulk faster than it could travel along the brain, is an open theoretical question. Some models of higher dimensional physics suggest that gravitational waves, which propagate through the bulk in these models, might travel through extra dimensions in ways that effectively appear superluminal from the brain perspective. The challenge with extra dimensions as a route to faster-than-light travel is that they are currently entirely theoretical. We have no direct experimental evidence for extra dimensions at any scale. The Large Hadron Collider at CERN has searched for signatures of large extra dimensions in high-energy particle collisions and found none, setting increasingly stringent limits on how large any extra dimensions could be. That does not rule out extra dimensions at the Planck scale, which is far too small to be probed with any current or foreseeable collider. But Planck-scale extra dimensions are also the hardest to use for any practical application, since accessing them would require energies 15 orders of magnitude beyond what our best accelerators can produce. There is something that is right now, at this very moment, making space expand faster than light in the far reaches of the universe. We call it dark energy. We do not know what it is, and its existence suggests something profound about the fundamental structure of the universe, something that might one day be relevant to the question of faster-than-light travel. Let us start with what we know. In 1998, two independent teams of astronomers studying type Ia supernovae, a specific kind of stellar explosion that always releases approximately the same amount of energy and can therefore be used as distance markers across the cosmos, discovered something that nobody expected. The universe's expansion is accelerating. Distant galaxies are not just moving away from us. They are speeding up as they move away. This was such a surprising result that the scientists involved initially thought they had made a mistake. They checked their data, checked their methods, and checked their assumptions again and again. The result held. The expansion of the universe is getting faster over time. This is the opposite of what you would expect from a universe governed only by gravity. Gravity pulls matter together. It should be slowing the expansion down, not speeding it up. For the expansion to be accelerating, there must be some other component of the universe that pushes space apart, that has a repulsive gravitational effect. This component is what we call dark energy. It accounts for approximately 68% of the total energy content of the universe. Ordinary matter, all the stars, planets, gas and dust we can see, accounts for only about 5%. Dark matter, which we infer from its gravitational effects but cannot directly observe, accounts for about 27%. Dark energy is the dominant component of the universe, and we have no idea what it is. The simplest hypothesis is that dark energy is what Einstein called the cosmological constant, a constant energy density of empty space itself, sometimes called vacuum energy. In quantum field theory, empty space is not truly empty. It contains quantum fluctuations, and these fluctuations carry energy. The energy density of the quantum vacuum, calculated theoretically, is something. Whether this vacuum energy is the same as dark energy is one of the biggest open questions in theoretical physics. In fact, there is a famous discrepancy. When physicists calculate the expected energy density of the quantum vacuum from quantum field theory, they get a number that's roughly 10 to the 120th power times larger than the observed dark energy density. That is a discrepancy of 120 orders of magnitude, possibly the largest discrepancy between a theoretical prediction and an observation in the history of science. This discrepancy is called the cosmological constant problem, and it is one of the greatest unsolved problems in physics. Now, what does this have to do with faster-than-light travel? Dark energy makes space expand. In the far future, dark energy will cause every region of space more than about 18 billion light-years from us to recede faster than light, permanently cutting off our view of those regions. Locally, in our galaxy and our local group of galaxies, gravity is strong enough to hold everything together. But on the largest scales, dark energy is winning. If we understood what dark energy actually is, if we understood the physics behind the accelerating expansion, we might understand the mechanism by which space itself can be made to expand or contract at arbitrary rates. And that understanding, in turn, might open pathways to controlled space-time distortion of the kind required for warp drives and other faster-than-light mechanisms. Some speculative theories of dark energy propose that it is not a constant but a dynamic field, called quintessence, that varies in space and time. If dark energy is a field, it might be possible to locally manipulate that field, changing the effective expansion rate of space in a controlled region. This is highly speculative, but it connects the phenomenon of cosmic acceleration to the possibility of local space-time engineering. In 2025, astrophysicist Jamie Farnes of the University of Oxford published a theory that proposes to unify dark energy and dark matter into a single entity he called a dark fluid, characterized by negative mass. This theory, if correct, would mean that negative mass, and therefore negative energy density in a broad sense, is not just a mathematical curiosity, but actually constitutes 27% of the universe. A universe containing a natural abundance of negative mass matter would be a universe where the exotic matter needed for warp drives and traversable wormholes might actually exist, just in a form we have not yet learned to collect or manipulate. This theory remains highly controversial and unconfirmed, but it illustrates how discoveries in fundamental cosmology can have direct implications for the question of whether faster-than-light travel is physically realizable. At this point in our journey, we have encountered a remarkable fact that keeps repeating itself in different forms. Every method of faster-than-light travel that physicists have proposed has one thing in common. It appears to also allow time travel. The Alcubierre drive, used cleverly, allows you to return before you left. The traversable wormhole, configured correctly, becomes a time machine. The Krasnikov tube, duplicated, creates a causal loop. Even tachyons, if they could be used to send information, would allow signals to arrive before they were sent in certain reference frames. This is not a coincidence. It is a deep feature of relativistic space-time. In Einstein's theory, space and time are not separate. They are woven together into a single four-dimensional fabric. Anything that allows you to traverse large distances of space in a short time also inevitably allows you to traverse large distances of time in a short space. In other words, to move backward in time. This is why the question of faster-than-light travel and the question of time travel are, at the deepest level, the same question. In 1992, Stephen Hawking proposed a resolution to this disturbing state of affairs. He called it the chronology protection conjecture. The conjecture states that the laws of physics conspire to prevent the formation of closed time-like curves, paths through space-time that loop back on themselves, from macroscopic objects. In other words, the universe protects causality. It does not allow time travel, and therefore it does not allow faster-than-light travel of the kind that would enable time travel. Hawking's argument was not that any specific mechanism prevents time travel. It was that quantum effects, specifically the radiation of virtual particles near the kinds of space-time structures needed for time travel, would generate catastrophic feedback loops that would destroy the structures before they could be used. The quantum vacuum, filled with virtual particle pairs, would create an insurmountable barrier against any attempt to create a closed causal loop. This is a physically reasonable argument. When you try to form a closed time-like curve, light from the future and past of the curve starts to pile up near the boundary of the curve's formation region, creating an increasingly intense beam of radiation. This radiation, called vacuum fluctuations, or Casimir radiation in this context, builds up in intensity as the curve approaches formation. According to Hawking, this build-up eventually becomes strong enough to destroy whatever structure was being used to create the curve. But the chronology protection conjecture is just that, a conjecture. It has not been proven. Physicist Kip Thorne and his colleagues analyzed specific traversable wormhole geometries in the early 1990s and found that, at least in certain cases, the quantum effects near the wormhole were not obviously catastrophic. Whether a full quantum gravity treatment, incorporating both quantum mechanics and general relativity simultaneously, would save or doom these structures cannot be determined without a complete theory of quantum gravity, which we do not have. Matt Visser, one of the leading researchers in traversable wormhole physics, has argued that the behavior of quantum fields near wormhole horizons is sufficiently uncertain, given our lack of a complete quantum gravity theory, that we cannot confidently say whether chronology protection holds. He calls the status of the conjecture still open. Some physicists have proposed that even if time travel to the past is allowed by the physics, paradoxes might be avoided by a principle of self-consistency. Any sequence of events involving time travel must be self-consistent with itself. This is called the Novikov self-consistency principle, after Russian physicist Igor Novikov. On this view, you could go back in time, but you could not change the past. Any actions you took in the past would turn out to be part of the history that already happened. The universe enforces consistency, not impossibility. Others argue for the many worlds interpretation of quantum mechanics, in which going back in time would branch off into a different quantum branch, a different version of history. So there is no paradox, because you are not changing your own timeline, only creating a new one. None of these arguments has been definitively resolved. The question of whether the universe permits time travel, and whether preventing time travel forces the universe to also prevent faster-than-light travel, remains one of the deepest open questions in theoretical physics. In 2011, a division of NASA called the EagleWorks Laboratories was established at the Johnson Space Center in Houston, Texas, under the direction of physicist Harold "Sonny" White. The purpose of EagleWorks was not to develop rocket fuel or build conventional spacecraft. It was explicitly to investigate breakthrough propulsion concepts, including specifically the Alcubierre warp drive. The United States government space agency was funding research into faster-than-light travel. This was not a large program by NASA's standards. It operated on a modest budget, but it was real. It produced peer-reviewed publications, and it represented perhaps the most serious government-funded effort to take warp drive physics from pure theory to something closer to an experimental science. White's main contributions were twofold. First, his theoretical work on reducing the energy requirements of the Alcubierre drive. By modifying the shape of the warp bubble from a flat shell to an oscillating toroidal shape, White argued that the required exotic energy could potentially be reduced from something equivalent to Jupiter's mass energy to something closer to the mass energy of about 700 kilograms of matter. This was a dramatic claimed reduction, though other physicists questioned the validity of the approximations used. Second, and more provocatively, White built an experimental device called the White-Jude warp field interferometer. The idea behind this device was to generate a tiny warp bubble, not large enough to move anything, not even close to the scale of interstellar travel, but large enough to produce a detectable signature, and then use laser interferometry to measure it. Laser interferometry is extraordinarily sensitive. It is the same technology, at a much larger scale, that LIGO uses to detect gravitational waves from colliding black holes billions of light-years away. White believed that even a microscopic space-time distortion, if generated, would be measurable with a sufficiently sensitive interferometer. EagleWorks reported some interesting results that White suggested might be consistent with a tiny warp field. But these results were never definitively confirmed, and the broader physics community received them with significant skepticism. The signals detected were small enough that alternative explanations, vibrations, thermal effects, electromagnetic interference, could not be ruled out. EagleWorks has since been scaled back, and White himself left NASA to work at a private company. But the program, even if it did not produce definitive results, demonstrated something important, that warp drive physics is not so obviously impossible that serious scientists are unwilling to pursue it experimentally. The current state of play in practical warp drive research is a mix of theoretical progress and continued experimental stagnation. We have better mathematical models. We have a richer understanding of the space of possible warp geometries. We have some proposals for how to reduce energy requirements, but we have no experimental confirmation of any warp-related phenomenon, and the gap between our current technology and anything approaching a macroscopic warp bubble remains astronomically large. Everything we have discussed so far has been situated within the framework of general relativity, Einstein's theory of gravity, sometimes combined with quantum mechanics, but never in a fully unified way. And that is the problem. General relativity and quantum mechanics are the two most successful theories in the history of physics. General relativity describes the large-scale structure of the universe: gravity, space-time geometry, black holes, the Big Bang, with extraordinary precision. Quantum mechanics describes the behavior of matter and energy at the atomic and subatomic scale with equally extraordinary precision. Together, they have made predictions confirmed to more decimal places than virtually any other theories in science. And yet, they fundamentally contradict each other. Not in any experiment we have done. Both theories make accurate predictions in their respective domains, but their mathematical foundations are incompatible. General relativity is a classical theory. It describes smooth, continuous fields and deterministic evolution. Quantum mechanics is based on probability, discreteness, and fundamental indeterminacy. Combining them in a mathematically rigorous way has proven to be the central unsolved problem of theoretical physics for the past century. The theory of quantum gravity, a theory that successfully unifies general relativity and quantum mechanics, does not yet exist. String theory is the most developed candidate, but it remains unverified by experiment and incomplete in important ways. Loop quantum gravity is another candidate with a different approach. There are others. None has achieved the status of a confirmed scientific theory. Why does this matter for faster-than-light travel? Because all of the exotic phenomena we have discussed, exotic matter, traversable wormholes, warp bubbles, the chronology protection conjecture, quantum tunneling, the nature of space-time at small scales, depend critically on the correct theory of quantum gravity for their ultimate resolution. Consider exotic matter. In classical general relativity, there is nothing inherently impossible about matter with negative energy density. The Casimir effect shows that quantum mechanics produces negative energy densities in certain situations. But can negative energy be produced in the quantities needed for a warp drive or wormhole? The answer depends on what quantum field theory tells us about the vacuum state in curved space-time near these extreme structures. And fully answering that question requires a working theory of quantum gravity. Consider the traversable wormhole. Classical general relativity allows the solution. Quantum mechanics allows the Casimir effect, which produces negative energy. but whether a traversable wormhole could exist in a universe described by quantum gravity. Whether the quantum fluctuations of space-time itself would destabilize the structure at the scales involved depends on the quantum gravity theory. Consider the Alcubierre drive. The classical solution exists. The energy conditions needed are specified. But whether those energy conditions can be satisfied in a quantum theory, whether quantum gravity allows or forbids the relevant exotic energy states, is unknown. Consider the chronology protection conjecture. Hawking based his argument on the behavior of quantum fields in curved space-time near potential time machine structures. But his calculation was semi-classical. It treated space-time classically and matter-quantum mechanically. A full quantum gravity treatment might give a different answer. This means that the deepest question, not can we build a warp drive today, but does the physics of the universe ultimately allow faster-than-light travel, cannot be definitively answered until we have a working theory of quantum gravity. And this is both frustrating and exciting. Frustrating because it means we cannot close the question. Exciting because it means the question remains genuinely open. String theory has some tantalizing hints. In string theory, space-time is not the fundamental object. It emerges from the dynamics of strings, which are one-dimensional objects vibrating in a higher dimensional space. The space-time we observe is a low-energy approximation. At extremely high energies, at the Planck scale, the nature of space-time changes fundamentally. It becomes granular, uncertain, subject to quantum fluctuations at the scale of the Planck length. In this picture, the properties of space-time that we take for granted, its topology, its dimensionality, even the existence of a definite speed limit, are emergent, approximate features that might be different in high-energy or extreme curvature situations. If space-time is not fundamental but emergent, then perhaps its properties, including the cosmic speed limit, are not absolute laws, but effective rules that apply in ordinary circumstances and might be modified in extreme conditions. This is speculative, but it is the kind of speculation that theoretical physicists take seriously because it comes with mathematical tools and specific frameworks that can be analyzed and tested. The connection between string theory, extra dimensions, and faster-than-light travel is direct. String theory requires 10 or 11 dimensions. Those extra dimensions at the Planck scale provide alternative paths through the multidimensional space that includes our observable universe. If those paths can be accessed, a very big if, they could provide effective, faster-than-light shortcuts. String theory also contains objects called D-branes, higher dimensional analogues of membranes on which the ends of strings can be attached. Our universe might be a three-dimensional D-brane embedded in a higher dimensional bulk. The dynamics of D-branes and the strings connecting them might, under certain conditions, allow for processes that appear superluminal from the three-dimensional brain perspective. None of this is worked out in sufficient detail to constitute a proposal for a faster-than-light drive. but it represents a genuine theoretical framework within which faster-than-light physics might be naturally accommodated, in ways that do not necessarily violate any deeper principles. We have mentioned the Casimir effect multiple times as the only known laboratory-scale phenomenon that produces negative energy density. Let us now examine it in the detail it deserves, because if there is any hope of producing exotic matter at scales relevant to warp drives or wormholes, the Casimir effect is where that hope begins. In 1948, Dutch physicist Hendrik Casimir was working on problems in quantum electrodynamics when he derived a remarkable prediction. Two uncharged, perfectly conducting, parallel plates placed very close to each other in a vacuum would experience an attractive force pulling them together, despite the fact that they have no net electric charge and there is nothing between them. This force arises because of the quantum vacuum. Empty space is not truly empty in quantum field theory. The uncertainty principle, one of the foundational results of quantum mechanics, implies that energy cannot be perfectly zero in any region of space. There are always quantum fluctuations, virtual particle pairs popping into existence and annihilating almost immediately, everywhere, all the time. These virtual particles are real in the sense that they have measurable effects. The Casimir force is one of those measurable effects. Here is what happens. Between the two closely spaced plates, the spectrum of vacuum fluctuations is restricted. Only virtual photons with wavelengths that fit evenly between the plates, where the plates are separated by distance d, only wavelengths of 2dd, 2/3 d, 1/2 d, and so on, can exist in the gap. Outside the plates, all wavelengths can exist. This means there is more vacuum energy outside the plates than between them. The difference in vacuum energy creates a pressure imbalance, and the plates are pushed together by the excess vacuum pressure from outside. The region between the plates has a lower energy density than the surrounding vacuum. In technical terms, it has negative energy density relative to the vacuum state. This is the only form of negative energy density that has been experimentally confirmed. The force has been measured precisely. In 1997, Steve Lamoureux at the University of Washington measured the Casimir force between metallic surfaces and confirmed it to 5% accuracy. Subsequent measurements have confirmed it to better than 1% accuracy. The Casimir effect is real, reproducible, and extremely well understood. The energy densities involved are tiny. For plates separated by 1 micrometer, 1/1,000,000th of a meter, roughly the scale of a bacterium, the negative energy density is approximately minus 1.3 times 10 to the minus 3 joules per cubic meter. For comparison, the energy density of a nuclear weapon is on the order of 10 to the 19th joules per cubic meter. To get useful amounts of negative energy for a warp drive, you would need to scale up the Casimir effect by many, many orders of magnitude. Physicists have thought about ways to enhance or scale the Casimir effect. One proposal involves using exotic materials called metamaterials, engineered materials with unusual electromagnetic properties that can amplify certain effects. In certain metamaterial configurations, the effective electromagnetic environment can mimic closely spaced conducting plates over a much larger volume, potentially producing larger Casimir-like negative energy densities. This is speculative and has not been demonstrated at any significant scale. Another idea involves dynamic Casimir effects. The standard Casimir setup involves static plates. If you move the plates very rapidly, accelerating them at enormous rates, you can create real photons from the vacuum, a process called the dynamical Casimir effect, first confirmed experimentally in 2011. Whether dynamical Casimir processes can produce useful quantities of negative energy on the scales needed for anything related to warp drives remains entirely unclear. There is also the question of what physicists call quantum energy inequalities. These are mathematical results, derived rigorously within standard quantum field theory, that set limits on how much negative energy can exist in a given region of space for a given period of time. The basic idea is that negative energy states in quantum field theory are always accompanied by positive energy elsewhere, and the integral of energy over time is bounded from below by a positive number. You cannot borrow too much negative energy for too long without paying it back in positive energy. These quantum energy inequalities are a serious obstacle to exotic matter production for warp drives. Thorne, Ford, Roman and others have shown that for any warp drive of macroscopic size, operating for any significant duration, the total amount of negative energy required would violate these inequalities, meaning it is more than quantum field theory could possibly produce. However, and this is a recurring theme in this story, quantum energy inequalities are derived within the framework of quantum field theory in curved space-time, not within a full quantum gravity theory. Whether they survive in a complete theory of quantum gravity is unknown. In 2024, a team of theoretical physicists published a paper in Physical Review D that took the question of warp drives in a fascinating new direction. Instead of asking how to build one, they asked what would happen if one already existed somewhere in the universe and broke down. Their conclusion? A collapsing warp bubble would generate gravitational waves, ripples in the fabric of space-time, that would propagate outward through the universe at the speed of light and could, in principle, be detected by gravitational wave observatories here on Earth. This is significant for several reasons. First, gravitational waves are now routinely detected. Since LIGO made its first detection of gravitational waves in 2015 from the merger of two black holes, gravitational wave astronomy has grown into a thriving observational science. LIGO, Virgo and Kagra have now detected dozens of gravitational wave events from colliding black holes and merging neutron stars. Second, the gravitational wave signature of a collapsing warp bubble would be distinctive, different from the gravitational waves produced by merging black holes or neutron stars. In principle, a sufficiently advanced analysis of gravitational wave data might be able to identify the signature of a warp bubble collapse and distinguish it from astrophysical sources. Third, and most remarkably, this means that warp drives are now, in principle, detectable from Earth. If any civilization anywhere in the observable universe ever built and then lost control of a warp drive, we might, under the right circumstances, detect the gravitational wave signature of that event. This connects the question of faster-than-light travel to the search for extraterrestrial intelligence in a completely new way. SETI, the search for extraterrestrial intelligence, has traditionally focused on detecting radio signals or optical signals from distant civilizations. The gravitational wave approach adds a new channel. Even if an alien civilization did not intentionally send us a message, their technology might inadvertently announce itself through gravitational wave signatures. The researchers were careful to note that the sensitivity required to detect a warp bubble collapse would depend strongly on the size of the bubble and its distance from Earth. For events within our galaxy, future gravitational wave detectors, particularly the planned space-based detector LISA, a 3 million kilometer triangle of spacecraft scheduled to fly in the 1930s, might have the sensitivity to detect warp bubble signatures if they exist. This is not a proven detection capability. It is a theoretical analysis of what the signature would look like. But it establishes that warp drive physics is not forever beyond the reach of observation. There are specific, predictive signatures that follow from the physics, and those signatures might be observable with current or near-future technology. Here is something that most people do not know. The speed of light in a vacuum, approximately 299,792,458 meters per second, is the cosmic speed limit. But light does not always travel at this speed. When light passes through a medium, glass, water, air, it slows down. In water, light travels at about 75% of its vacuum speed. In glass, about 65%. In certain special materials called Bose-Einstein condensates, light has been slowed to less than 17 meters per second, slower than a bicycle. This means that particles moving through those media can actually exceed the speed of light within those media. When a charged particle, an electron for instance, travels through a medium at a speed greater than the speed of light in that medium, it emits a characteristic blue-white glow called Cherenkov radiation. This radiation is the optical equivalent of a sonic boom, the same basic physics, but for light instead of sound. If you have ever seen photographs of the interior of a nuclear reactor, the eerie blue glow around the fuel rods is Cherenkov radiation from electrons moving faster than light in water. But this is not true faster than light travel. The particles are still moving slower than the speed of light in vacuum. They are faster than the local light speed in the medium, not the universal cosmic limit. However, there is a quantum analogue of this that is more interesting. In the 1988 paper by physicist K. Scharnhorst, an effect was proposed in which light travelling between Casimir plates, in the region of lower than vacuum energy density, would travel slightly faster than light in ordinary vacuum. This is because the reduced virtual particle density between the plates allows light to propagate with slightly less interaction, and therefore slightly faster. The effect Scharnhorst calculated is fantastically small. For realistic plate separations, the difference in speed would be around 1 part in 10 to the 24th. far too small to measure with any conceivable current technology. And subsequent analyses suggested that even if the effect is real, it might not actually allow signals to travel faster than light in a causality-violating sense due to subtleties in how the wave-front velocity behaves near the plates. But the Scharnhorst effect illustrates something conceptually important. The speed of light is not a fixed property of space itself, but a property of the quantum vacuum state of space. In regions where the vacuum state is different, as it is between Casimir plates, the effective speed of light is slightly different. If you could modify the vacuum state on a large scale, you might, in principle, modify the local speed of light in a way that changes what faster than light means in that region. This is another way in which the Casimir effect connects to the broader question of faster-than-light travel. The vacuum state of space is not fixed and immutable. It can be modified, at least on small scales. Understanding how to modify it on large scales, and whether doing so can produce effects relevant to superluminal travel, is an open research question. To understand why exotic matter with negative energy density might or might not exist, we need to go deeper into the quantum field theory picture of the vacuum. In the 1920s and 30s, physicists including Paul Dirac worked out the quantum theory of the electron, what we now call quantum electrodynamics, in embryonic form. Dirac's equation for the electron was a stunning achievement. It naturally incorporated both quantum mechanics and special relativity. It correctly predicted the electron's spin, and it led directly to the prediction of antimatter. But Dirac's equation had a problem. It produced solutions with negative energy. Not just small negative energies, arbitrarily large negative energies. An electron could apparently fall into states of lower and lower negative energy without limit, radiating energy endlessly. Physically, this would mean matter would be unstable. Electrons would cascade into ever lower energy states, releasing an infinite amount of energy, which obviously does not happen. Dirac's solution was audacious. He proposed that all the negative energy states were already filled, that the vacuum of space is a sea of electrons occupying every possible negative energy state. This is called the Dirac sea. Because all the negative energy states are already filled, a real electron cannot fall into them. The Pauli exclusion principle, which prevents two fermions from occupying the same quantum state, blocks the cascade. If this is right, then a hole in the Dirac sea, a missing negative energy electron, would behave like a particle with positive energy and the opposite electric charge. This was the prediction of the positron, the antiparticle of the electron, which was discovered experimentally by Carl Anderson in 1932. The prediction was completely confirmed. Now, in modern quantum field theory, we do not usually talk about the Dirac sea explicitly. The formalism has been updated. But the conceptual legacy is important. The vacuum of space is not nothing. It is a structured quantum state with specific properties. It has an energy, the zero-point energy of the quantum fields that fill space. And this energy, while it cannot be directly harvested, influences the behavior of matter and radiation in measurable ways. The key point for our purposes is this. The energy of the quantum vacuum is not a simple, fixed number. It varies depending on the boundary conditions, on what is nearby, what fields are present, how space is curved. The Casimir effect is one consequence of this variability. The negative energy density between Casimir plates is a real consequence of the boundary conditions set by the plates changing the structure of the quantum vacuum in the gap. If you could create different boundary conditions on a larger scale, not just two parallel plates, but an extended region of controlled vacuum structure, you might be able to engineer regions of negative energy density that are larger and more intense than anything the simple Casimir effect provides. Whether this is possible in principle, and if so, what scale of negative energy density could be achieved, depends on the details of quantum field theory in curved space-time and ultimately on quantum gravity. Some theoretical proposals for generating larger Casimir-like negative energies involve topological modifications of space, changing the connectivity of space in a small region, rather than just the boundary conditions on existing space. This is deeply speculative, but it connects to ideas from quantum gravity and string theory about the discreteness and quantum nature of space-time at the Planck scale. We have now surveyed the full landscape of serious scientific proposals for faster-than-light travel. The Alcubierre warp drive, traversable wormholes, tachyons, quantum entanglement, quantum tunneling, the Krasnikov tube, the Lentz drive, extra dimensions, dark energy manipulation, the Scharnhorst effect, Casimir energy engineering. It is worth stepping back and looking at what these proposals have in common, and what they tell us about where the real obstacles lie. First observation: most of these methods do not actually require anything to move faster than light through flat, ordinary space-time. The Alcubierre drive moves space-time. The wormhole is a shortcut through space-time. Extra dimensions provide a shorter path. Even the Krasnikov tube works by distorting the shape of space-time rather than moving through it. The cosmic speed limit, the rule that nothing can exceed c, applies to objects moving through undisturbed space-time. Physics does not explicitly forbid the distortion of space-time itself. In fact, space-time distortion is exactly what general relativity describes and what we observe every day in the form of gravity. Every mass distorts space-time. Every gravitational wave is a ripple of space-time distortion. The universe is constantly doing space-time engineering. The question is whether it can be done in the specific configurations needed for faster-than-light travel. Second observation: the fundamental obstacle in almost every case is exotic matter, matter with negative energy density. The Alcubierre drive needs it to create the warp bubble. The traversable wormhole needs it to keep the throat open. The Krasnikov tube needs it to maintain the distorted region. Even the Lentz drive, which claims to avoid it, may still need it at the boundaries. This is not a coincidence. It follows from a deep mathematical result in general relativity called the energy conditions. These are mathematical inequalities, constraints on the energy density and pressure of matter that must be satisfied for space-time to have certain reasonable properties. One of them, called the null energy condition, states that the energy density, as measured by any observer moving at the speed of light, must be non-negative. This condition, if satisfied, prevents various pathological behaviors of space-time, including faster-than-light travel. In other words, general relativity tells us that if you want to do faster-than-light travel, you must violate the null energy condition. And violating the null energy condition means using exotic matter with negative energy density. The two requirements are, at a fundamental mathematical level, the same requirement. The question is whether the null energy condition can be violated in a real physical theory. In classical general relativity, no known matter violates it. All known forms of matter satisfy it. In quantum field theory, the null energy condition can be violated locally. The Casimir effect does it. But quantum inequalities constrain how much and for how long. In a complete quantum gravity theory, we do not know. Third observation: every route to faster-than-light travel also potentially enables time travel, and the universe may have a self-consistency mechanism, Hawking's chronology protection or something equivalent, that prevents both simultaneously. If chronology protection holds, then no form of faster-than-light travel that enables time travel is permitted by physics. Since, as we have seen, all known forms of faster-than-light travel appear to enable time travel, chronology protection would effectively forbid all of them. But chronology protection is a conjecture, not a theorem. It has not been proven. And the proof of it, if it exists, requires a theory of quantum gravity that we do not yet have. Fourth observation: there may be no method of faster-than-light travel at all. The universe may simply be structured in such a way that it is physically impossible. And this would not be the end of the story for interstellar travel. Even without faster-than-light travel, interstellar travel is not necessarily impossible. Time dilation offers a genuine, experimentally confirmed effect that can make very long journeys subjectively short for the traveler. A spacecraft moving at 99% of the speed of light would experience time at about 14% of the rate experienced by observers at rest. A journey of 100 light years would take only 14 years of subjective time for the crew, even though it takes over 100 years of time for everyone else. At even higher fractions of light speed, the time dilation becomes more extreme. At 99.9% of light speed, the Lorentz factor is about 22. So a journey of 1,000 light-years takes only about 45 years of subjective crew time. At 99.99% of light speed, the Lorentz factor is about 224, making a journey of 10,000 light-years take only about 45 subjective years. This is not faster-than-light travel. It is not instantaneous, but it is a genuine, relativistically permitted route to interstellar distances within human lifetimes. The obstacles are technological and energetic. Getting a spacecraft to 99% of light speed requires enormous energy by current standards. But they are not fundamental physics obstacles. This brings us to the present, to where the science actually stands right now in the opening months of 2026. The honest summary is this: We have not gotten dramatically closer to a practical faster-than-light drive since Alcubierre's 1994 paper. But the theoretical landscape has grown significantly richer, more nuanced, and in some ways more optimistic in specific and qualified ways. On the warp drive front, the most recent developments include Lenz's 2020 work on positive energy warp geometries, the Bobrick-Martire framework for classifying all warp drive spacetimes, and ongoing theoretical work on reducing energy requirements and understanding the radiation environment inside warp bubbles. None of these constitute a breakthrough that brings a warp drive closer to reality, but they represent a maturing of the theoretical understanding, a clearer picture of what the constraints actually are and what would be needed to satisfy them. On the wormhole front, the ER equals EPR conjecture continues to generate research connecting quantum information, entanglement, and space-time geometry. The 2022 quantum computer simulation of wormhole dynamics at Caltech, while controversial in its interpretation, inspired a wave of follow-up theoretical work. And the 2026 paper reinterpreting Einstein-Rosen bridges in quantum terms adds a new perspective that might eventually have implications for traversability. On the quantum gravity front, several research groups are making progress on understanding how space-time behaves at the Planck scale, using a variety of approaches, including string theory, loop quantum gravity, and causal dynamical triangulations. These are theoretical advances that do not immediately translate to practical faster-than-light proposals, but they are building the foundation of understanding that any serious faster-than-light theory will eventually need to stand on. On the energy side, scientists are continuing to study Casimir systems and related phenomena. There is ongoing research into dynamic Casimir effects, Casimir-Polder interactions, and the possibility of engineering vacuum states with unusual properties using metamaterials and other engineered structures. The energies involved are still many orders of magnitude below what is needed for any warp drive or wormhole, but the fundamental physics is being understood with increasing precision. There is also a significant research program in what might be called sub-warp exotic propulsion. Propulsion concepts that do not require faster-than-light travel, but that significantly exceed the efficiency and speed of conventional rocket propulsion. These include ion drives, solar sails, laser-pushed light sail concepts like breakthrough starshot, nuclear pulse propulsion, and antimatter propulsion. Some of these could potentially accelerate spacecraft to a few % of the speed of light. Not faster than light, but fast enough to reach the nearest stars in decades rather than millennia. The Breakthrough Starshot initiative, announced in 2016 and still ongoing, aims to develop a laser propulsion system that could accelerate a very small, light spacecraft, essentially a tiny chip, to 20% of the speed of light using a powerful ground-based laser array. At that speed, the craft could reach Proxima Centauri in about 20 years. It would not carry humans. It would not be returning. But it represents the most concrete current proposal for actually sending something from our solar system to another star within a human lifetime. We have spent this entire documentary focused on the physics. But it is worth pausing at the end to consider what faster-than-light travel would actually mean, not just as a technology, but as a fact about the universe. If faster-than-light travel is possible, several things follow immediately. First, the universe is fundamentally more navigable than it appears. The cosmos is not a vast, hostile expanse that eternally imprisons every species on its home planet. It is a network of accessible places connected by paths we have not yet found, but that do exist. The apparent isolation of civilizations across cosmic distances is an illusion born of our current technological limitations, not a permanent feature of reality. Second, time travel may be possible. As we have discussed repeatedly, faster-than-light travel and time travel are, within the framework of relativity, deeply connected. If one is possible, the other may be as well. And time travel, if possible, raises questions about causality, free will, and the structure of history that go far beyond physics into philosophy, ethics, and the nature of reality itself. Third, the Fermi paradox. The question of why, given the vast number of stars and planets in the universe and the potential age of many civilizations, we have seen no evidence of extraterrestrial intelligent life, becomes even more urgent. If faster-than-light travel is possible, a sufficiently advanced civilization could have colonized the entire galaxy in a few million years. The galaxy is 10 billion years old. Where is everybody? The Fermi paradox is already puzzling. If faster-than-light travel is possible, it becomes deeply strange. Fourth, the physics underlying faster-than-light travel would represent a completely new domain of knowledge, a regime of physics beyond what we currently understand. The journey to faster-than-light travel would almost certainly involve discoveries that transform our understanding of space-time, energy, matter, and causality in ways we cannot yet foresee. The history of physics suggests that the biggest technological revolutions have always been preceded by fundamental conceptual revolutions, new ways of thinking about what reality is. If faster-than-light travel is not possible, if the universe is indeed structured so that no physical system of any kind can travel faster than light, this too has profound philosophical implications. It means the universe is compartmentalized into regions that are permanently isolated from each other. Any civilization is, in the deepest sense, alone in its corner of the cosmos, able to observe distant regions but never reach them. The observable universe becomes the definitive universe, and everything beyond the cosmic horizon is not just unseen, but unreachable and ultimately irrelevant. Either answer, possible or impossible, is extraordinary. The physicist John Wheeler, who coined the term wormhole and who spent his career thinking about the deepest questions of physics, once said something that resonates here. He said, "We live on an island of knowledge surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance." Faster-than-light travel is one of the places where our island meets the sea. We can see the shore clearly. We can see some of the features of the water nearby. We have mathematical tools for exploring further. But we do not yet know what is out there. Let us now do something that no documentary on this subject usually does. Give you a clean, honest, up-to-date verdict on every single method we have discussed. The Alcubierre warp drive, mathematically valid within general relativity. Requires exotic matter with negative energy density which may or may not exist at the required scale. Energy requirements may be reducible but remain enormous. Navigation and radiation problems unsolved. Would likely enable time travel. Status: theoretically possible within classical general relativity, outcome in quantum gravity unknown, practically unrealizable with any known or foreseeable technology. Traversable wormholes, mathematically valid within general relativity. Require exotic matter, can potentially be created from quantum vacuum effects like the Casimir effect, but far below required quantities. Would function as time machines if properly configured. The ER equals EPR conjecture suggests deep connections to quantum entanglement that may provide new theoretical pathways. The 2026 work on Einstein-Rosen bridges in quantum terms opens new interpretive possibilities. Status: theoretically possible, practically unrealizable, actively researched, deeply connected to foundational questions in quantum gravity. Tachyons: mathematically describable within special relativity using imaginary rest mass. Would violate causality if used to send information. No experimental evidence for their existence. Tachyonic fields, fields with imaginary mass, do appear in the Standard Model, most famously the Higgs field before symmetry breaking. But these are not the same as tachyonic particles that travel faster than light. Status: ruled out as practically useful by causality concerns, not absolutely ruled out by current physics, unlikely to exist as free particles in nature. Quantum entanglement. Real phenomenon, experimentally verified to extraordinary precision. Quantum correlations are genuinely instantaneous over arbitrary distances. Cannot be used to transmit information faster than light, because the correlations cannot be controlled. The no communication theorem prevents information transfer. However, the ER equals EPR conjecture suggests entanglement and wormholes are related, and if that connection can be exploited in a quantum gravity framework, it might eventually be relevant to superluminal communication. Status: real but currently incapable of transmitting information faster than light. Possible future relevance in quantum gravity context. Quantum tunneling. Real phenomenon used in technology daily. The Hartmann effect produces apparent superluminal peak velocities of wave packets through barriers. However, careful analysis suggests the signal front, the actual causal edge of the wave, still travels at or below the speed of light. The question of what tunneling time means is genuinely unresolved and is still being actively investigated. Status: real phenomenon, apparent superluminal effects explained by wave packet reshaping in standard theory, genuinely unresolved at a foundational level. No practical application to faster-than-light travel currently apparent. The Krasnikov tube. Mathematically valid within general relativity. Similar requirements to the Alcubierre drive. Exotic matter, enormous energy. Solves the navigation problem of the Alcubierre drive. Would likely enable time travel. Less studied than the Alcubierre drive or wormholes. Status. Theoretically valid, practically unrealizable, historically important as an alternative warp drive geometry. The Lentz drive, published in 2020, proposes a warp drive geometry using only positive energy density. Disputed by other physicists who argue it may still require exotic energy at boundaries. Even if exotic matter-free, the energy requirements remain enormous. Cannot achieve faster than light speeds without some form of exotic energy, according to the Bobrick-Martyr framework. Status. Represents a real theoretical advance, disputed in detail, does not resolve the fundamental problem of faster-than-light travel. Extra dimensions. Theoretically well motivated in the context of string theory and other higher dimensional theories of gravity. If extra dimensions exist at any scale, they provide alternative paths through space-time that could be shorter than paths through our observable three-dimensional space. No experimental evidence for extra dimensions at any currently accessible scale. Practical access to extra-dimensional paths is entirely speculative. Status. Theoretically motivated, experimentally unsupported, not ruled out at the Planck scale. Dark energy manipulation. Dark energy is real. The accelerating expansion of the universe is observed. We do not understand its nature. If dark energy is a dynamic field, controlled local manipulation is in principle conceivable. Completely speculative, with no known mechanism. Status, real phenomenon, complete mystery as to mechanism, speculative connection to faster-than-light travel. The Scharnhorst effect, theoretically derived, predicts light travels slightly faster than vacuum light speed between Casimir plates. Effect is so tiny as to be unmeasurable. Whether it actually allows signal velocity to exceed c is disputed. Status, theoretically interesting, practically irrelevant at current understanding. The Casimir effect as exotic energy source. Real and well measured. Produces genuine negative energy density at tiny scales. Quantum energy inequalities constrain how much negative energy is available and for how long. Far below the scales needed for warp drives or wormholes. Whether quantum gravity changes the constraints is unknown. Status. Real effect, relevant in principle, vastly insufficient in practice, limitations possibly modified by quantum gravity. We have come a long way. We started with a wall, the cosmic speed limit, built into the fabric of space-time by the mathematics of special relativity, confirmed by every experiment ever performed. We then catalogued every serious scientific attempt to get around that wall. Not through it, but around it, underneath it, through tunnels in it, through extra-dimensional highways that bypass it entirely. And we found, repeatedly, that the universe seems to have placed these methods behind a locked door labelled, first, find exotic matter, and second, figure out quantum gravity. So is faster-than-light travel possible? The honest answer is, we do not know. And that answer genuinely, scientifically, legitimately we do not know, is not a cop-out. It is the most accurate statement of the state of the science. We know that the laws of physics, as currently understood, do not permit it in any practical sense. Every known method requires either exotic matter we cannot produce, energy we cannot generate, or physics we do not yet understand. We know that the laws of physics as currently understood might not be complete. We do not have a theory of quantum gravity. We do not understand dark energy. We do not know whether exotic matter exists at the scales needed. We do not know whether the chronology protection conjecture is true. We do not know what happens to the energy conditions in a full quantum gravity theory. In every previous era of physics, there were things that the laws of physics said were impossible, which turned out to be possible once the laws were better understood. Powered flight was considered impossible by some 19th century physicists who had not yet accounted for the right aerodynamic effects. Nuclear energy was considered impossible before the discovery of fission. The existence of black holes was considered impossible, even by Einstein himself, who published a paper in 1939 arguing that they could not form. He was wrong. None of these examples prove that faster-than-light travel is possible. They do not even make it likely. The history of physics is also full of things that were suspected to be possible, but turned out to be permanently forbidden. Perpetual motion machines, for example, which are prohibited by the laws of thermodynamics, no matter how clever the design. The speed of light barrier is more fundamental and more thoroughly tested than almost any other limit in physics. But here is what we can say with confidence. The question is not closed. The mathematics of general relativity does not explicitly forbid it. The equations that govern our universe, the same equations that predicted the existence of black holes, gravitational waves, and the expansion of the universe, all of which were confirmed by experiment, also contain solutions that look like warp drives and traversable wormholes. Those solutions are there in the mathematics, whether we can build them or not. The universe has already, demonstrably, exceeded the speed of light in the expansion of space. The speed limit is not absolute for space-time itself. What remains unknown is whether that flexibility of space-time can be harnessed for deliberate controlled transport. The absence of proof is not the proof of absence. We have not been able to demonstrate that exotic matter cannot exist at the required scale. We have not been able to prove the chronology protection conjecture. We have not yet developed a theory of quantum gravity that could settle these questions definitively. And this means that the possibility, however remote it may seem, remains open. The physicist Miguel Alcubierre himself, when asked about the practical prospects of his warp drive, said something that captures the spirit of this entire endeavor perfectly. He said that he published the paper not because he thought anyone was going to build a warp drive next year, but because he thought it was important to know whether the laws of physics, in principle, allowed it. Because that question, does the universe permit this, is one of the most profound questions science can ask. We are, all of us, passengers on a pale blue dot, circling an ordinary star, in an outer arm of an ordinary galaxy. in a universe so vast that the light from its most distant regions has been travelling toward us since before the Earth existed and has still not arrived. For most of human history, that vastness was incomprehensible and irrelevant. We could not see it, could not measure it, and could not conceive of travelling into it. Now, in this brief instant of cosmic time, we are a species that has mapped the observable universe to 14 billion light-years, that has sent spacecraft to the edge of the solar system, that has landed on the moon, that has detected gravitational waves from colliding black holes, that has imaged a black hole directly, that has found thousands of planets orbiting other stars. We are a species that for the first time can ask the question of whether faster-than-light travel is possible. Not as mythology, not as science fiction, but as a scientific question with mathematical structure, testable predictions, and real, ongoing research. That is not nothing. That is, in fact, everything. The universe is not going to tell us easily. It never has. But the history of science is the history of problems that once seemed permanent being solved by minds that refuse to accept permanent. We do not know if we will ever travel faster than light. We do not know if we will ever fold space, traverse a wormhole, ride a space-time wave to the stars. What we do know is that the question is real. The physics is real. The mathematics is real. The researchers working on it are real. And somewhere in the vast space of what we do not yet know about quantum gravity, exotic matter, and the deep structure of space-time, somewhere in that vast unexplored territory, the answer is real too. We just have not found it yet. Before we finish, let us spend a moment with the numbers. The raw, unadorned numbers that make the question of faster-than-light travel not just interesting but necessary for any civilization that wants to be something more than a local phenomenon. The distance from Earth to the nearest star, Proxima Centauri, 4.2 light-years, or approximately 40 trillion kilometers. At the speed of the fastest current spacecraft, it would take approximately 75,000 years to get there. The diameter of the Milky Way galaxy, approximately 100,000 light-years. At the speed of light, it would take 100,000 years to cross it. The distance to the Andromeda galaxy, our nearest large galactic neighbor, 2.5 million light-years. At the speed of light, 2.5 million years. The diameter of the observable universe, approximately 93 billion light-years. At the speed of light, 93 billion years. The universe is only 13.8 billion years old. These are the numbers that make the cosmic speed limit feel like a permanent exile. And these are the numbers that make faster-than-light travel, however difficult, however remote, however physically uncertain, feel like the most important unsolved problem in all of science. Not because we will solve it tomorrow, not because the obstacles are small, but because the stars are out there. And we are the kind of creatures who look at them and refuse to accept that we can never reach them. The journey toward those stars, the journey of understanding the physics that governs the very possibility of that journey, has barely begun. This is where we are. This is where the science stands. And this, for now, is where we leave you.